In this lecture, we shall study about the heat and work and the first law of thermodynamics. One of the main subjects in thermodynamics is the physics of gases. A gas consists of atoms that fill their container's volume and exert pressure on the container's walls. We can usually assign a temperature to such a contained gas. These three variables associated with a gas are volume, pressure, and temperature. These are all a consequence of the motion of the atoms. The volume is a result of the freedom the atoms have to spread throughout the container. The pressure is a result of the collisions of the atoms with the container's walls. And the temperature has to do with the kinetic energy of the atoms. The kinetic theory of gases, the focus of this chapter, relates the motion of the atoms to the volume, pressure, and temperature of the gas. Applications of the kinetic theory of gases are countless. Automobile engineers are concerned with the combustion of vaporized fuel, a gas, in the automobile engines. Food engineers are concerned with the production rate of the fermentation gas that causes bread to rise as it bakes. Beverage engineers are concerned with how gas can produce the head in a glass of beer or shoot a cork from a champagne bottle. Environmental scientists are concerned with how heat exchanges between the oceans and the atmosphere can affect weather conditions. The first step in our discussion of the kinetic theory of gases deals with measuring the amount of a gas present in a sample, for which we use Avogadro's number. Okay, let us look at heat and work. We know heat is a form of energy. Here we look in some detail at how energy can be transferred as heat and work between a system and its environment. Let us take our system a gas confined to a cylinder with a movable piston. Okay, let us suppose that we have a container here. This is a piston. Lead shorts, and this is the system, the gas. These are valves. Insulated valve. And this is a heat, thermal reservoir. The upward force on the piston, you see the piston here. The upward force on the piston due to the pressure of the confined gas is equal to the weight of lead shot loaded onto the top of the piston that I have shown here. The walls of the cylinder are made of insulating material that does not allow any transfer of energy as heat. The bottom of the cylinder rests on a reservoir for thermal energy. This is thermal energy, a thermal reservoir, perhaps a hot plate whose temperature capital T you can control by turning a knob. The system, the gas, starts from an initial state I described by a pressure Pi, a volume Vi, and a temperature Ti. Let us say there is a initial state I, and we have a final state F. Now we have the state variables, and these are pressure, Pi, volume Vi, and temperature Ti. It's the initial state. Now, after the change of the state, in the final state, let us say the pressure is Pf, volume is Vf, and temperature Tf. The procedure by which we change this system from its initial state I to its final state F is called a thermodynamic process. Okay, so by thermodynamic process, we can go from initial state I to final state F. During such a process, energy may be transferred into the system from the thermal reservoir, positive heat, or vice versa, negative heat. Also, work can be done by the system to raise the loaded piston, positive work, or lower it, negative work. We assume that all such changes occur slowly, with the result that the system is always in thermal equilibrium. That is, every part of the system is always in thermal equilibrium with every other part. Let us suppose that we remove a few lead shot from the piston of this figure. Allowing the gas to push the piston and remaining shot upward through a differential displacement small d. Okay, so if this piston goes to this direction, a small distance d with an upward force. Since this displacement is very tiny, we can assume that the force is constant during the displacement. Then has a magnitude of the force which is equal to magnitude of the force will be pressure into area of cross section of the cylinder. Force F will be P into A. Pressure, and A is the area of cross section of the cylinder. Or we say container in the form of a cylinder. The differential work done uh, by the gas during the displacement is, you can say, dW equal to force into displacement. So this, and this force F into the direction of the force and the displacement in the same direction, so is this, and we can write this pressure into area of cross section, and the displacement is ds. So we can write down this A into ds. So it's a volume element, A into ds. You can write down is dv, the volume element, area of cross section, and into distance ds. And ds is the displacement Now, to get the total work done, we'll have to integrate this relation. By the gas from volume Vi to volume Vf is and this is P into dV. During the volume change, the pressure and temperature may also change. To evaluate this equation, let us say this is 1 and this is 2. We would need to know how pressure varies with volume. So we need to know the pressure as a function of volume. There are actually many ways to take the gas from state I to state F. One way is shown in this figure that I am drawing now. I'm now drawing one of the ways that by which we can go from the initial state to final state. This is volume, let us say this is pressure, and say this is initial state I and this final state F. Now gas moves from say I to F doing positive work. So the amount of work will be this, the area under this curve IF with the volume axis. So this is the work done and W is positive. We can have another way. We can go from initial state I to final state F. Let us say this is our initial state I and final state F, and we can go from I to A, say small a, and keeping pressure constant, and then go from A to F, keeping the volume constant. So the work done by the gas, which is positive, and will be this. So this is one way. This is another way. There are some other ways we can go from initial state I to the final state F. So when the work done is positive, that means we say that the work is being done by the gas. Okay, another way we go from initial state I to final state F is this. So we keep the volume constant and then keeping the pressure constant. So the work done will be this. And here also the work done is positive. The fourth way we go from initial state I to final state F is okay, let us say this is G, this point is G, and this point is F. Okay, H. Let's say this is H, and we can also go from this initial state I to say point C, and keeping the volume constant, and then keeping the pressure constant. So if we go by this way, I, G, H, F, then the work done will be very large. The area under this curve, I, G, H, okay, with the volume axis. And if we go from this way, I, C, F, then the work done will be much smaller. It will be the area under the curve CF with the V axis. You can have another way. We can go from initial state I to final state F. Actually, we go from F to I. That means we reduce the volume. Here the system goes from state F to state I as the gas is compressed, because now the volume decreases to less volume by an external force, and the work W done by the system is now negative. That means this amount of work, but this will be negative because the work done on the system, because the volume decreases, and that is why the work is negative. In those figures, work is positive, but here work is negative. And finally, we have another way. We can go from you see initial state I to the final state F, and then come back to I again. Okay, so we go from this way and come back to I along this way. So there will be a net work done. Okay, we are coming back to I. Starts from I, goes to F along this way, and coming back to I from F this way. So the net work done is positive. Okay, now we shall discuss about the first law of thermodynamics. We have just seen that when a system changes from a given initial state to a given final state, both the work W and the heat Q depend on the nature of the process. Experimentally, however, we find a surprising thing. The quantity Q minus W, Q is the amount of heat that is being absorbed by the gas in the container. If this is positive, and if heat is being given out by the gas to the thermal reservoir, then Q will be negative. W is the work done by the gas, amount of heat absorbed, and this is done by the gas. This quantity remains constant. Remains constant means it does not depend on path. So when you go from state I to state F, whatever the path, this quantity does not depend. Is fixed for all the paths. It depends only on the initial and final states and does not depend at all on how the system gets from one to the other. All other combinations of Q and W, including Q alone, W alone, or Q plus W and Q minus twice W, are path dependent. Only the quantity Q minus W, it is path independent. The quantity then Q minus W must represent a change in some intrinsic property of the system. So you see the Q minus W does not depend on path, but depends only on the initial and final states. Q minus W must represent a change in some intrinsic property of the system. That property is usually known as the internal energy of the system. Thus, we can write change in the internal energy is E internal energy final minus E internal energy initial, and which is equal to Q minus W. This is the first law of thermodynamics. The first law of thermodynamics is an equation which can be applied to solve several problems. It should be mentioned here that in the differential form, this equation can be written as from the first law of thermodynamics. Can be written as dE internal is equal to dQ minus dW. It should be mentioned here that the internal energy E int of a system tends to increase if energy is added as heat Q and tends to decrease if energy is lost as work W done by the system. We know from the principle of energy conservation as it applies to isolated systems, that is to systems in which no energy enters or leaves the system. The first law of thermodynamics is an extension of that principle to systems that are not isolated. In such cases, energy may be transferred into or out of the system as either work W or heat Q. In our statement of the first law of thermodynamics above, we assume that there are no changes in the kinetic energy or the potential energy of the system as a whole. That is, change in kinetic energy and potential energy is zero. There are no changes in the potential energy and kinetic energy. That is, the work done on a system is always the negative of the work done by the system. So if we rewrite this equation in terms of the work W done on the system, we can write actually, okay, instead of this one, if we rewrite this equation, then we can also write down delta E int equal to Q plus W, and this is, we say, on, means work done on the system. This tells us the following: the internal energy of a system tends to increase if heat is absorbed by the system or if positive work is done on the system. Conversely, the internal energy tends to decrease if heat is lost by the system or if negative work is done on the system. This is for today. In the next lecture, we shall discuss some special cases of the first law of thermodynamics.